Hi. Cool. So thanks everybody for coming. This talk is called Morph Your Malware. And yeah, my name is Sebastian. I'm working as a red team operator at a company called Code White. We're basically doing all sorts of red teaming, purple teaming, also regular pen tests, but we're specialized on red and purple teaming. My main part in the team is the creation of offensive tools and probably most importantly, the creation of a custom C2, which we're using in our assessments. And this talk is about the execution and the hiding of malware in the context of another process. We will be taking a look at techniques which are typically used by adversaries to avoid detection either by security products or by analysts which are manually taking a look at processes which might be infected. And we will be trying to fingerprint infected processes simply by looking at the memory, the states of certain threads, and by taking a look at the call stack of certain threads. I then show you, or I will try to give you an idea of how to avoid being fingerprinted by blending in with false positives or by using a bit more advanced techniques. So 2 slides of general talk. Why does it actually matter? For us, red teams, protecting and hiding our tools definitely has priority for 2 reasons. The first reason is that we obviously do not want to get caught. If we get caught, then the operation is pretty much ruined. We didn't fulfill the goal. The second reason is that custom tooling is quite complex and also precious. Those of you who are developing their own C2 know that it's a quite painful task and it might take ages to achieve it. Dropping tools on disk is obviously considered an OPSEC fail. Operators tend to forget their tools on disk, which is a big problem because security solutions are really good at analyzing stuff that you ever put on disk. But even more important, like for real, operators forget what they stored on disk at some point. The thing with in-memory malware is that it needs a host process, otherwise it wouldn't work. You cannot simply choose any process that you like, notepad.exe for example, that doesn't make any sense. Why? Because usually the process that you're injecting your tool into, the behavior of this process should be as similar as possible compared to the tool that you're injecting. For example, it doesn't make any sense to inject a Cobalt beacon into Notepad. Why? Because Notepad usually doesn't have any internet connections, right? So you will have to carefully choose the host process based on does it make any internet or internet connections, is it making use of DP API, or is it even probably known to legitimately access elders. I personally like to target browsers because they're doing pretty much all of this. And the thing with process injection is that it's nowadays quite heavily monitored, and this is what this talk is going to be about. So how does it work? Basically it works in 3 steps. The first step being that you kind of need to open a handle on the process that you're trying to inject into. A handle basically allows you to perform certain operations on the process that you're trying to fiddle with. The second step is then to kind of somehow inject the payload that you're trying to execute. So you need to write code into the context of another process. And the last step is that you somehow need to make the process into which you're injecting to actually execute the payload. So once again, first step, handle creation. The most obvious way to do this is to simply make use of an API call called open process. You specify a PID, you specify a process access mask, and depending on if you have the right permissions on the process that you're trying to access, you will be given a handle. There are a bunch of problems with this approach. The first, or the big problem is that upon process access, there's a kernel callback, meaning that the kernel is going to notify every single driver which is subscribing to this kernel callback about this process is actually opening another process with this access mask, which makes the creation of a new handle quite easy to observe for security products because of this kernel callback. And this is why you have the sysmon event, which is letting you know that scratchpad.exe is opening notepad.exe in this case. A probably better way would be to make use of a concept called handle duplication, and it basically works as follows. The observation is that there are multiple processes on Windows, and there might even be a process which is already holding a handle on the process that you're trying to inject into. That means that everything you need to do is you need to open the other process which already holds a handle to the process that you're trying to inject into, duplicate or steal this handle from the other process and then reuse it in another context. Like this, you're kind of shifting the problem away from opening the target process, but you're opening another process. Last year, I released a tool which is called HandleCats. It leverages this exact technique to obtain a handle to else's, and it went pretty well by bypassing a bunch of security products because there's no process access event anymore on else's, right? There's a big problem with this approach, however, and this approach is that there is not always a suitable handle pre-existing on the system that you infected, so it's not really reliable. What is probably a bit less known is that existing handles can also be upgraded. This means that you can basically create a new handle on the target process with a very limited access mask, which doesn't show your real intent. And before you actually use it, you duplicate it once again. And when you duplicate it, you say, well, the duplicated version of this handle, it would be nice if it had another process, another access mask. This is really cool because there's no suspicious process access event. There's only the duplication of a pre-existing handle with another access mask. This is quite cool because there are kernel callbacks for handle duplication, but Sysmon, for example, is not subscribing to this kernel callback. You can still observe this in the Windows security log, but the problem with this is that it must explicitly be configured per process, and it's not enabled by default. So I really like to go with this approach in order to get a handle to another process. The thing is that obtaining a handle was only the first step, right? I showed you 3 steps that we need to do. The first step was actually not that difficult. The real problem starts, we now need to use our newly created handle in order to inject the payload into another process. How do we do this? The problem with this is that there are a bunch of security techniques trying to make your life more difficult. So, for example, you guys might have heard of a concept called userland hooks. There are even more kernel callbacks, and there's also event tracing for Windows. Let us first talk a bit about userland hooks and system calls. This is a quite old concept, and it's being widely used and exploited in the security scene, but for those of you who might have never heard of, 2 slides of theory. The thing is that antivirus really like to redirect the execution flow of suspicious API calls. They do so that they understand when a certain API call was used by a process and with which parameters it was used. They do so because they do not really have any other chance to understand when a certain API call is used. There's not a kernel callback for every single system call there is. This used to be true. We will later get to how it is nowadays. And the thing is that system calls, which are usually used for process injection, are obviously hooked because the antivirus product is quite interested in why this API is actually used and how it is used. So basically, if you're making use of, if you're trying to create a remote threat, the malware is going to go through the abstraction layer in the kernel 32 DLL, which is then calling something in the anti-DLL, and the anti-DLL is then going to perform the system call for you. Yeah. If there's a userland hook in place, the first steps are similar. You still go through kernel DLL, you then go to anti-DLL, and last but not least, you end up in the antivirus DLL, which is then doing some analysis for you. There are some obvious ways to bypass userland hooks, and there are 100,000 ways probably. The most obvious way to bypass this is to directly conduct a system call, and this is doable by simply embedding the code snippets of the anti-DLL into your own malware, and then letting your malware actually do the system call for you, which effectively bypasses kernel 32, anti-DLL, and the other antivirus DLL. However, I mean, it does bypass userland hooks, but there are some very obvious problems with this approach. The obvious problem is that all system calls should go through anti-DLL. If any other module than anti-DLL is doing a system call, then this is quite suspicious, because this should actually never be the case. And if you take a look at Sysmon, in the upper screenshot, we see the usage of the Windows API, and we see that the last module in the call trace is actually anti-DLL. But if we make use of direct system calls, here I use the tool by Outflank. Hello. We see that the last module in the call trace is actually not anti-DLL, but it's Outflank dumper DLL, which is a big indicator of compromise, I'm assuming. The problem, however, is that, yes, you can sometimes observe direct system calls using sysmon, but there are not kernel callbacks for every single system call there is. There's one for NT-open process, but there are way more system calls you guys might be interested in. And since there is no kernel callback for every single system call, you might want to use an additional framework. And an additional framework which you might be leveraging is called Nirvana, which is an instrumentation engine used by Microsoft. It's present in Windows since Vista. It's a quite complicated thing, and I'm not going to get into too many details here, but it can actually be used to monitor and control user-made processes without recompiling the target. More importantly, it even allows us to define callbacks for system calls upon return from kernel mode. And what that means is that we can basically specify if a system call returns from kernel mode, it should, before it continues the execution in user mode, it should execute our user-specified callback. And this actually allows us to hook basically every single system call and perform some additional code before it transitions back to user mode. More importantly, it allows us to check where the system call is returning in user mode. If it's not returning to somewhere in NTDLL, then this is obviously an IOC. And there's a really cool sample implementation by WinTernal, and if we make use of this implementation, again, against outflank dumped, the implementation by WinTernal, I think it's called syscall detect, is immediately complaining that the kernel returns to an unverified module and it's going to exit. So this can actually potentially be used by security products in order to identify direct system calls. It's just that the performance overhead might actually be a big issue here. So what can we do against this? Obviously, we need to make sure that our system calls go through NTDLL and bypass userland hooks at the same time. And the cool observation is that an antivirus product does, of course, not hook every single system call there is, otherwise it would also run into performance problems. It only hooks those system calls it's actually interested in. This leaves us to the observation, or this brings us to the observation that some system call stubs are simply not hooked because the API calls are simply not interesting enough. Yet, all system call stubs do pretty much the same thing, but they use a different system call number. So basically, they move the system call number to EAX and then perform the system call by syscall read. What can we do? The idea could be to first resolve the system call number by using a technique called haloscate, which is by Sector 7. And then we initialize the system call manually, and then we reuse existing syscall read instructions from a clean system call stub in order to perform the system call. So we basically jump to a very certain location of a clean system call stub, which is the system call read instruction. We basically reuse these instructions from a clean system call stub. So I'm a paint master. We first set up the registers, then we kind of reuse the stub, once again, meaning that we choose a clean system call stub, which is not hooked, and then reuse the system call read instructions from there, which effectively bypasses the userland hooks, and we're going through NTDLL at the same time. I wrote a small implementation for this. You can find it on my GitHub. And if I make use of this and I use the syscall detect tool at the same time, it's not complaining. Why is it not complaining? Because the system calls, they all return to NTDLL. And you see in sysmon, the last module on the call stack is NTDLL. There are still some IOCs though, because usually system calls go through kernel-based DLL and then to NTDLL. This is the first IOC. The second IOC is that, yeah, the system call returns to NTDLL, but it does not return to the correct stub, which is associated with the executed system call. And by leveraging hooking Nirvana, this might be an idea in order to leverage this. Cool. So userland hooks are still a thing in 2022, actually, and I was quite surprised about this because I thought it's like a relic from the past, but that's not the case. Many antivirus security products still rely heavily on them, and the question is why. The first reason is that monitoring from kernel only can cause stability issues, because if you fuck up your kernel driver, then your client won't be protected, but has a blue screen. And the second problem was, this is not the case anymore, but it was that missing telemetry, because there was no other way for an antivirus to understand if and how a certain API call was used. So it was used kind of a patch to get more telemetry. What matters from the attacker's perspective is basically that userland hooks are not a problem. They can always be efficiently and stealthily bypassed, and GitHub is full of userland hook bypassing techniques. Cool, so now we should be able to conduct memory operations on the remote process with the handle we gained earlier in a very stealth way. So we should be able to inject our payload using every single API call we want. Is that true? And the thing is, we still need to keep some facts in mind, because some system calls trigger a kernel callback, as I was saying before, and others can actually be observed by ETW, because there's a ETW provider which many security solutions have begun subscribing on, and it's called the Microsoft Windows Threat Intelligence ETW provider. The provider sits in kernel, so there's not a lot you can do against this from user mode. And for us, it's kind of a problem because it delivers events for everything that might be used for process injection. You know, APCs, suspending threads, resuming threads, and so on and so on. So it should provide enough telemetry in order to observe typical process injection techniques, and there are a bunch of device event action types you can use. I tried to write rules for this for a client, for a very big client in a purple teaming assessment. And yeah, you can see the process injection. It's just that these API calls are so often used in a legitimate context that it's almost impossible to write a working detection rule for this without having any false positives. So what actually matters in my opinion is which process injects into which other process, and more importantly, what is actually being injected. If you inject a plain cobalt beacon into another process in the most stealth way, it will still be picked up simply because it's cobalt. So our next problem is actually static signatures, and we need to think about how to avoid static signatures or evade static signatures. Okay, once again, we successfully injected our payload into the target process, and obviously now Yara rules are applied by security products in order to identify if it is something they already know. And there are multiple ways to bypass this. Some are better than others, but let us take a look at this. The first concept is called polymorphism. It's a very old concept. What you're doing is basically you encrypt your payload and you glue it together with a decryption stub. The decryption stub decrypts the payload and then actually executes it. Cool. So here we have a hello world.bin, which basically pops up a message box, and we remember it starts with ASCII VH something something. If we put it into executable memory, it pops a message box and we see the VH something something in the executable memory page. Cool. Now if we make use of Shikata-Ganai, which is a polymorph encoder, we see that, yeah, it looks really different. It doesn't start with VH and there is no VH something something anymore because it's encrypted. But what happens if we actually execute it in memory? We see that the first bytes are different, but at some point our VH something something pops up once again. And we wanted to avoid this, wasn't it? So there are a bunch of problems with polymorphism. First, it needs RWX, which is an indicator as such. Second thing, the decryption stub as such can be fingerprinted. And after decryption, your malware or your tool or whatever is not protected in plain in memory. So it might help to bypass the initial memory scan, but at some point if the memory scan happens like, I don't know, 20 minutes later, your cobalt beacon or whatever is going to be plain in memory. Cobalt makes use of or tackles this problem with a concept called sleep mask. It was introduced in version 4, the 3 is wrong, it's 4 something. And the core idea is actually quite simple. The observation is that a beacon basically spends most of the time sleeping and waiting for new commands. So what you can do is, while sleeping, the beacon actually obfuscates and encrypts itself in memory while it is sleeping. And you must be quite unlucky if the memory scanner hits you right in the situation where your beacon is active, because usually a beacon is active only for, I don't know, a fraction of a second or something like that. There are some limitations with this, however, because the first limitation might be that the sleep mask itself can be fingerprinted. You can customize this in cobalt. And we also have other memory artifacts which we will take a look at later. I, however, like to use another concept. And the idea is to change the appearance of a program on instruction level. If we change the appearance of a program on instruction level, we do not need any encoding or encryption or whatever, and we do also not need any RWX because we're not encrypting anything. There are multiple ways to achieve this. One way to achieve this is to substitute instructions with a sequence of instructions which lead to the same result, yet these are other instructions. What you could also be doing is add useless instructions, or add trash and a jump over the trash, or you shuffle the basic blocks or whatever. The terminology for this is quite unclear for me. If you Google this, some actually call it a variant of polymorphism, others call it metamorphism. In this talk, we call it keyless polymorphism. So some ideas for substitutions. If you want to null out a register, either you can write XOR ix, or you move 0 to ix, or you store another register on the stack, null out this register, move this register to ix, and then restore this register. If you want to jump to RCX, you could also write push RCX and then return, where push RCX could also be written like this. So there are a bunch of ideas or instructions which can be substituted with an equivalent of other instructions. By adding trash, as I said, basically you add complete trash bytes or instructions which don't make any sense at all, and you add a jump over the trash. And however you do it, in the end of the day, so on the left side we see our actual program, which is not obfuscated or whatever, and on the right side we see that the first instruction was substituted with another instruction, second one is also substituted, then we have a jump over the trash, then probably an instruction which could not be substituted, and last but not least, another substitution. I really like to leverage this technique to protect my tools from automated memory scanners, and it's quite powerful if enough instructions are substituted. You obviously need the source code for this, because otherwise you would be breaking relative gems. And if you consider this to be a problem, it makes your payload obviously significantly larger. Also, you need to take into consideration that strings and constants need to be encrypted and obfuscated additionally, because this is not part of the polymorph process. Doing this by hand is really, really annoying, and you should automate this. I will later get back to how to automate this. Cool. So once again, we remember our VH something something shellcode that pops a message box. And here, if we use this keyless polymorph concept, we see that it actually doesn't start with VH anymore. Actually, you don't find these constants anymore in an executable memory page, yet the message box still pops up. If there's someone really careful, you see that this is actually in an RWX page. I earlier said you don't need RWX. It's because I forgot to change the page permissions. Cool, so now we gained a handle in a very stealthy way. We defended userland hooks while still we go through NTDLL, and we defeated scanners using some kind of polymorphism. The problem now is that infected processes leave a lot of other IOCs. So even if you manage to infect a process that you wanted to infect, you still have a lot of other IOCs. Let us take a look at suspicious artifacts. To understand this, some basics. Windows roughly has 3 types of memory. There's private committed memory, which is reserved for heap and stack. There's map memory, which is used for file mapping and IPC. And there's also image committed memory, which is basically used by PE files and executables. And the thing is that usually only image committed memory should be marked as executable. There are some false positives, or there are some exceptions. For example, managed code like C#, because it's bytecode which is compiled, interpreted at runtime. But as we see on the screenshot, actually only, or normally only, image committed memory should be marked as executable. And this gives us a big problem, because somehow we need to gain executable memory while injecting into a remote process. And the problem is, how do we actually get executable memory in a remote process? And there are a bunch of memory scanners which are really, really good at finding memories or abnormal memory allocations. The one by Moneta is really popular, and they're really good at detecting abnormal memory allocations. So for example, if you make use of virtual alloc or anti-map view of section or whatever, Moneta is quickly complaining about, hey, there are 2 pages which are marked as executable, yet they are marked as private commit. What the fuck is this? That doesn't make any sense. The next try could be to make use of DLL hollowing, where we load an unused DLL into the remote process and then replace the text segment with our own code. Problem, Moneta is complaining again. Why? For 2 reasons. First, Moneta is asking, why did this process load this DLL? It's not declared in the PEB or anywhere. Why did it decide to load this DLL? Second problem, the text segment of the DLL on disk is not the same as the text segment of the DLL in memory. It's also a big problem for Moneta. And There are a bunch of ways to bypass memory scanners, and they basically all boil down to changing the page permission of the beacon while it's actually sleeping. Because memory scanners only check for executable memory regions in order to find known bad. This brings us a big problem, because how do you mark your own code as not executable while you're executing? This should not actually happen. This should not work. But it does work with a bit of black magic, and I like to leverage a concept used by exploit coders, which is called return-oriented programming, which leverages stack pivoting and existing small code snippets from any NTDLL or other executable memory which is there legitimately. So the idea is, before the beacon goes to sleep, we set up a rob chain which first calls virtual protect, marking our beacon as not executable. Then it robs itself to sleep, and then it robs itself again to page execute read. This is nothing new as such. The original idea was called Gargoyle. I'm assuming it was first implemented by F-Secure, but I'm not sure about this. And the core idea here is that before we go to sleep, we set up the stack, and we set up the stack as follows. The first return address on the stack points to a gadget which sets up the registers, or which pops the other values on the stack in a certain way, and in such a way that on the next return, when virtual protect happens, the address of the beacon is not marked, or the page of the beacon is not marked as executable anymore. So upon the next return, our beacon looks like this. It's not executable anymore. And the stack looks like this. And now the first gadget on the stack points to a pop RCX gadget, which effectively puts the 5000 on the stack to RCX, which is the first parameter for sleep, and then it pops the return address of sleep and goes to sleep for 5000 milliseconds. Now the beacon is not executable and it's sleeping at the same time. And when the beacon returns, obviously it takes the first return address from the stack, again setting up the registers for virtual protect, which then, upon returning, makes our beacon resuming. I released a small proof of concept for this, which I call Deep Sleep. It's also on my GitHub. While it is active, it's actually popping a message box, and monitor complains. Why? Because there is private executable memory or something. But while sleeping, we see that the page of Deep Sleep is actually marked as not available, or execute read-only. Yeah, read-only makes sense. So we bypass memory scanners looking for executable memory. There are a bunch of other implementations. They all boil down, once again, to the same idea, which is changing the page permissions while sleeping. There's one by Cracked Spider, there's one by SecIdiot called Foliage. Yeah, but they are all pretty much boiled down to the same idea. Now, the question is actually, this was quite complicated, and the question is that actually necessary? And I would say no, because if you run monitor on Firefox, for example, you see a bunch of false positives once again. So you also see in Firefox that there is a bunch of private and executable memory, and it even modified its own DLL, its own NTDLL. So I believe that memory artifacts alone are a quite good first indicator, but they have way too many false positives. For example, why did Firefox change its own NTDLL? It's because it likes to hook its own create thread as a matter of an anti-exploit mechanism. Memory scanners can also be bypassed using Gargoyle-like techniques, and so the problem is that we definitely need more metrics in order to identify infected processes. Once again, the observation is that beacons spend most of the time waiting for new commands. And what developers really like to do to make the beacon sleep is to simply call sleep. This is really obvious, right? But there's a big problem with sleep. And the problem with this API call is that it sets this thread which is calling sleep to a very special state. It's called delay execution. And on my machine, I had 1,500 threads. Out of these 1,500 threads, and only 20 were in the state delay execution. So we boiled down from 1,500 to 20 threads, which might be a beacon. 20 are still too many to check, so we need another metric. The next metric could be a call stack. On the left side, we see a normal call stack. We see that it starts somewhere in user thread start, and it can map every return address on the stack to a module on disk. On the right side, we see the one of a cobalt-like beacon, and we see that it does not start where it's supposed to start, and at the same time, there is this hex 1A. What is this? This cannot be associated with a file on disk, because this is quite abnormal. And if you take a look at the implementation of Gargoyle, also of the deep sleep thing, the call stack looks even more broken because there are a bunch of pointers which cannot be mapped to a file on disk, and it looks like virtual protect is calling sleep. If you show me a developer who does this legitimately, I want to talk to him. So yeah, call stacks are also a thing. And now the question is, out of the 1,500 threads I have on my machine, how many of these are in delay execution and have a stack trace to delay execution which contains unknown or tempered regions? The answer is only one, and it's a beacon. So also for this, I created a small tool to automate these steps. It's called Hans Sleeping Beacons, and it first enumerates threads which are in delay execution, and then it checks the call stack for unknown regions and also for text segments which do differ compared from the in memory compared to the version on disk. Yeah, it picks up deep sleep because the thread is in delay execution and the stack is really, really broken. I had some false positives with this approach. I had false positives with updaters, which are trying to protect itself because they're actually behaving like a beacon. You know, they're also trying to obfuscate themselves in memory because they don't want you to reverse it. At the same time, they're also sleeping between their intervals. And I also had some false positives with very crappy C# applications. There are some other very easy bypasses for unsleeping beacons. The first idea could be to simply spoof the call stack, which is actually not very easy if you want to do it correctly. But the more easy way would even be to simply don't use sleep to wait between your callbacks. You can also make use of waitable timers in order to have a bit of delay. This then sets the thread in a state called wait user request, which is way more common than delay execution. Cool. So call stacks definitely leave significant IOCs, and this does not only apply to delay execution, but it also applies to other system calls. Memory scanners can actually fully be bypassed using Gargoyle or Gargoyle-like techniques, and C2 coders should definitely avoid using sleep. Internally for my C2, I use a modified version of Deep Sleep, which is using waitable timers. Cool. This is almost the end of my presentation. I have some tools to release. Earlier we were talking about keyless polymorphism. I created a tool to automate this step, which I call spider pick. And it actually does the obfuscation on assembly level. So what you do is you first compile it using GCC or whatever and you make the compiler output assembly. Then you make that spider pick do its job. It's doing the obfuscation, and then you compile it just as normal. And in order to show how greatly this actually works, we're also releasing a SOX proxy, which is implemented as position-independent code. The client makes use of WebSockets and is implemented as pick. And the spider pick is integrated into Makefile. So it looks differently every single time you compile the client version. The backend is written by my colleague and good friend Christian. And yeah, you can find it on our GitHub. So if every time you compile Lastenzug, you see that the fuzzy hash is completely different, yet they are all the same program. You can find it here on our GitHub. I think my boss clicked on release right now, and you simply type make to build it. Okay, that's it.